Hello and good afternoon friends, welcome once again to the CEC-UGC live lecture. Dear friends, as you know that from time to time we cater to your need by conducting lectures on such subjects which are specially demanded by you. So dear friends, this is another session on chemistry, and as you know that we have started with the series on chemical thermodynamics. This is the second lecture in the series, and today we would be talking on expansion work in thermodynamics, and for this we have again with us in our studios Dr. Amit Kumar. Dr. Kumar is Senior Assistant Professor in Department of Chemistry, Dayal Singh College, University of Delhi. So dear friends, let's take advantages from his experiences and try to understand the topic expansion work in thermodynamics. Hello sir, welcome to the EduSet lecture.
Thank you
As we have conducted previous session, also in previous session we conducted one of the lectures on chemical thermodynamics only, and this is the another lecture but with a fresh topic, that is expansion work in thermodynamics. So over to you sir.
Thank you very much, Kritika. And again, first of all, let me wish a very good afternoon to all my listeners. Dear friends, as we have covered in the first lecture, there are a number of topics. Let us have a quick recap of those ones. What we had covered is starting with just the definitions of simple terms such as systems surrounding boundaries. We defined the nature of boundaries, categorized them, and explained how the nature of the boundaries is defining the type of system. So with the description of a number of systems, the types of systems, thereafter our focus was on how the change in state of system is being brought about. Once we understand the state of system and the change in state, then of course we have understood how the change in state is being brought about. That is what we call as the path of change in state. So we defined state change, the state, and the path followed for the change in state of system. Apart from this, we also then defined, while we observe a change in state, change in number of properties, physical properties of system is observed. So all these physical properties are recognized as various parameters and are numerically quantified with the help of designating symbols. And these ones have been classified into two types, the state functions or the path functions, and we defined their characteristics. We tried to find out how the change in state is being observed to classify it as a state function or it as a path function. Following which, whenever a change in state has been brought about by a sequence of steps, we call it a process. Thereafter, depending upon the physical conditions prevailing in the system, we defined the types of processes also, depending upon which kind of variables or the functions were kept constant, which were varying. So depending on this, we defined the nature of processes, following which our focus was on the definition of the temperature, that is mainly through the description of zeroth law of thermodynamics. So this is all what we did up till now. Now let us see, we proceed now on with two important path functions which we described. One is the heat and the other is the path. So therefore, let us see, if when we defined the heat, we defined it as the transfer of energy which results or actually results in unorganized motion of molecules in the surroundings. Basically, suppose when we supply heat, what does it mean? That there are molecules in the surrounding which are migrating, and when colliding with the walls of the system, they are transferring their momentum, by virtue of which they are transferring energy. So this is called heat. Heat gets transferred to the system, that appears only across the boundary. Once it enters the system, how it manifests itself by virtue of some motions of the molecules of the system. If those molecules are in the gaseous state, then there will be random motion of molecules. So random motion will be can be considered as the kinetic motion of molecules, and we all know that the average kinetic energy is manifested as the temperature of the system. So, therefore, the energy which was transferred to the system as heat now is present in the system in the form of its internal energy by virtue of its temperature change. Similarly, is the situation with work. When work was done on the system, so energy was transferred, it again leads to the kinetic molecular motion of the constituent molecules within the system. So, with this we can say either the energy is transferred as heat or as work, it only leads to increase in internal energy of the system, or in particular we can say constituent molecules. So, let us now further understand, if not gaseous species, if suppose liquid species are there or solid species are there, they do not, the molecules within a solid species do not migrate as such. So, therefore, we must understand what kind of motions are excited upon, by virtue of which we can have a increase in internal energy. So, to say that when heat enters, it increases internal energy, as I said earlier. Let us now talk about solid system. We all know that in a solid state, the constituent chemical molecules are arranged in a sequence of steps, in a sequence of series. So, therefore, what happens is the vibrational motion of molecules are excited upon at fixed lattice sites of these molecules, which actually accounts for the vibrational motion, and by virtue of which we observe manifestation of temperature, that is, the temperature increases by virtue of supplying heat or adding work to the system. So, with this description, let us now, when we say heat and work, these are two important path functions. Now, today's topic is expansion work. So, why expansion work is considered important? Say for example, if you carry out a reaction in a closed vessel, what will happen? There may be a possibility of, suppose some solid species are interacting with liquids, or some liquids are interacting with some gaseous species, or whatever, they are producing further gaseous species. Then of course, as we all know, gases, whatever volume is accessible to gaseous species, they will occupy. So, therefore, the volume of the system will change during the course of reaction. So, there will be expansion, and we all know whenever work is being observed, it is at the expenditure of energy. So, while making consideration of energy changes in a reaction, we need to take expansion work also into account. Usually, however, we carry out chemical reactions in open vessels, usually where the pressure of the system always remain constant. So, let us now talk about expansion work. So, we first of all consider an expansion work. Let us first of all see what happens when a system, first of all let us define the system. System, suppose, is made up of a cylinder fitted with a movable piston. Now, in this figure you can see the piston is designated by symbol D, and this piston is enclosing within the inner walls of the system the gaseous species, and the gaseous species which is enclosed within the cylinder whose position is confined by the position of the piston itself, has a temperature T, the pressure P1 and volume V1. So, temperature T, pressure P1 and volume V1 do defines the initial state of the system. Now, when this system alters its volume against some opposing force, we say the work is produced, and in most practical situations it is the expansion work. Let us see how in this present system, which is shown in the figure, how we can observe expansion work. For consideration of this, let us say that there are set of stops S, these black stoppers which are being provided over here in figure A. These are set of stoppers which keep the position of the piston intact. And now suppose if we go to release these stoppers S, what will happen? The position of the piston may alter depending upon whatever is the pressure exerted externally on the system and what is internal pressure of the gas. If we all know that expansion work would be observed only under a gradient of pressure. So, therefore, we have also provided another set of stops. These stops are S dash. These stops are being provided, or stoppers are being provided just to ensure that when the system alter its volume from its initial volume V1, the piston will be held at this stops S dash and the volume of the system will get changed to value V2. If the pressure of the system, only when the pressure of the system will be greater than the opposing pressure. Now, let us understand how the opposing pressure is being exerted on the system. You see, it is important to understand whenever we consider expansion work by the cylinder piston arrangement, it is always considered that the space above the piston is evacuated, so that there is no other elements which can exert force except for a designated mass object M, which under the influence of gravity exerts a weight force, and this weight force actually bring about the external pressure, or we can say, since volume has to alter its position against this force, so we will call this force as opposing force. Now, since this force is being applied on the piston which has an area of cross section A, so therefore, we can say mg, the mass of the object, multiplied with the gravity, acceleration due to gravity, the gravitational field, this equals the pressure. This equals the pressure times the area of cross section, because work is what? Work is mass into acceleration due to gravity times the height h, that is the height to which the piston will get raised and will raise the mass object m, and this force, therefore, mg is equals the opposing pressure into A, the area of cross section of the piston. So, now when we substitute this equation 2 in 1, we get that work equals the P of opposing pressure times the AH. Now, what is AH? AH basically is the additional volume enclosed by the system when the volume changes of the system from initial volume V1 to volume V2. Now, so therefore, with this substitution of AH value in third equation, we get the value of work which is equal to P of opposing pressure times the difference in volume between final volume which is V2 minus the initial volume which is V1. So, this is how we get the value of expansion work. Now, you see, this expansion work would only be observed if there is a difference of pressure between the pressure inside the system and pressure outside the system. That is, the external pressure which is being exerted by virtue of this mass object M as shown in figure should be lesser than that of the internal pressure of the system, and moreover, there should be a limit to which this mass object can exert a pressure. This limit should not be greater than the final pressure of the system being achieved after the expansion work is observed. So, if now suppose with these conditions, if we release the set of stops S, now what will happen? Because of the difference or the gradient of pressure between the system and the surrounding, now because of greater pressure in the internal pressure of the system will alter its volume by virtue of change in position of its boundary, and this boundary is the piston which will actually move, and now the system will acquire a greater volume, will now enclose a greater volume. This increase in volume is known as additional volume being occupied by system during this change in state during the expansion process. Now, let us have a rationalization of this expansion process in the PV isotherm. In the PV isotherm basically is nothing but the pressure volume graph which is being plotted at constant temperature, and the PV isotherm curve is shown over here in the form of dotted curve. Over here you can see in the figure, this dotted curve actually the PV isotherm, and it represents both the initial state, the P1 V1 which is the pressure of the initial state, and volume V1 which is the volume of initial state, and moreover it also illustrates the pressure of the final state P2 as well as the volume of the final state V2. And we can see there are a number of points that are there on the dotted lines. This is how it shows that how the pressure as well as the volume is varying. Now, we have seen, let us now suppose that this mass object, as we have shown by virtue of calculation, is exerting a weight force, that is mg, and this weight force is exerted upon the area of cross section, and this force upon area which is actually, if we divide this mg by a, then becomes equal to the opposing pressure. So, in this graph we can see there is an opposing pressure. Now, the system alters its volume against this opposing pressure. So, therefore, P opposing, now this is this value shown by this point on the graph. Now, we can draw a horizontal line over here, and within this, beneath this line which we can draw from the range of volume V1 which is the initial state of system shown here to the final state of system shown here by this point, we can shed this area, and the shaded area is now representing the work which actually gets produced in the surrounding during this expansion process as we have defined over here. Now, having said this, there are certain conditions upon the pressure, opposing pressure. Now, there is a limit of opposing pressure. This opposing pressure can be either 0 or can be greater than 0, but should not be greater than the final pressure of the system, which the system we want to attain after in the final state. So, therefore, there is a condition of on opposing pressure, that is the opposing pressure should be greater than or equal to 0 or should also be less than or equal to final pressure of the system. So, therefore, we can say that if suppose we vary the mass object being placed on the system, so what it will vary? It will vary the opposing pressure which the system will against which the system will alter its volume. So, therefore, it means by variation in the mass object we are varying external pressure, but of course, within the limits between 0 and the final pressure P2. So, this opposing pressure which once we vary, so therefore, we can say a different path will be observed by the system, because in that situation different work will be observed. So, there is a limit. If we carry out the expansion work in one step, there is a limit of how much expansion work we can produce in one step. That is, the maximum limit is that it should be in the shaded area portion, that is when P opposing pressure is drawn at a point P2 value of pressure, that is over here. Now, you can see where I am moving the pointer, here we can draw a line, and therefore, this is the maximum shaded area we can draw in this single step process. Now, let us talk about what happens as to when we do not place a single mass object, the same mass object, rather we try to vary the opposing pressure and we carry out the whole expansion process in 2 steps. How 2 steps? That is, if suppose we now not apply the same mass object as we have done in single step, but let us now suppose we apply first of all external pressure by virtue of a mass object which is lesser. So, what will happen? The expansion will be this is the mass object. Let us suppose this mass object has greater mass first. So, what will happen? Now, the piston will alter its position and the volume of system will change, expansion work will be observed, but now it has to raise a greater mass object. In that situation, what we can see, for a change in volume from V1 to V dash, as you would see in figure over here, that would be greater as compared to for the volume change which is been for same change in volume in single step expansion. Now, so in first step we observe this much work, thereafter we will again observe expansion work from volume V dash to volume V2, and that work will now be against a lesser mass object, as in step 2 we will replace the mass object which we placed in step 1 by an mass object which will have lesser mass. So, therefore, we will have 2 steps, and in the 2 steps we will have 2 different amounts of work which when we do add up, they will account for the expansion work, which you can now see in the figure over here, how the expansion work in the PV diagram is different from that of the expansion work for the single step, and you can appreciate that there was a greater work which was done in a 2-step process. Now, if suppose we carry, and here you can see easily 2-step expansion process, you can compare this figure, the PV diagram for the 2-step expansion process, from that of the figure in the single step expansion process. Clearly, there was just a shaded portion which was here only, this you can see this shaded portion was only present. In addition, now we have some additional shaded portion over here. So, you can appreciate that compared to a single step process, if we carry out the same expansion process in the 2-step, we will observe a greater amount of work being produced in the surrounding. So, now let us talk about the multi-step expansion process. You see, in a multi-step expansion process, we will carry out the whole expansion process not just in 1 step, 2 step, 10 steps. Suppose in a very large number of steps, and the work produced in each step, if we do make a sum of the work produced in each step, that will account for the total work produced for same change in state from initial state P1 V1 to the final state P2 V2. And in that situation, we will have to make use of the integral calculus, and we can calculate the work as integral from initial volume Vi, the initial volume, to Vf, the final volume. Pext or P op, opposing pressure, is been the same thing. So, here I have written Pext, that is the external pressure times the dV. The small volume it will change, because you see if we carry out large number of the whole expansion process from V1 to V2, there will be large number of steps, and when there will be large number of steps, at each step only a very small change in volume will be observed, that is dV. And when we multiply opposing pressure, the Pext, with that of small change in the volume element dV, what we will get is the P external dV, the dW, smaller contribution of work in that small step. Now, if we add up the work involved in all those steps, we need to take an integral within limit Vi to Vf. So, therefore, this is how we can determine the work involved in the multi-step, a large number of expansion steps. Now, over here P, the opposing external pressure, you can see is not constant. There are number of steps, at each step we are replacing mass object, and therefore we are varying the external pressure. This external pressure will not be very different from that of internal pressure of the system at each step, but at each step it will be just little bit lesser than that of the internal pressure. So, you can see internal pressure, if we subtract from internal pressure the small value of pressure, that is dP, it amounts to external pressure. So, therefore, it means in a large number of expansion process steps, if the expansion process is carried out in a very large number, so what will happen is that external pressure will be slightly lesser than that of internal pressure. And now we can take the the integral terms as separate terms, and we can define two separate integrals, P int dV minus Vi Vf dP dV. Now, you can see the second term in this expression dP dV is basically an integral of two differentials, that is two very small quantities products. So, if we multiply two very small quantities, it will lead to a further smaller quantity. So, what we can say is the second term in comparison to the first term is very negligible, and so expansion work will only be represented by an integral from initial volume Vi to Vf P int dV, that is the internal pressure of the gas times the change in volume, which we need to integrate to actually find the work. And for that we need to actually, since the internal pressure is also changing during each step, we need to find out how the internal pressure is dependent upon the volume of the system, and correspondingly with the substitution of that expression, what we will be able to do is we will be able to calculate the expansion work involved in this multi-step expansion. As you did observe in the PV diagram, a comparison when we make of single step expansion with that of two step expansion. In two step expansion there was greater work which was involved, and in a multi step expansion process, now you can see the shaded area is just lies below that of the PV expansion curve. So, therefore, this is the greatest value of work which is involved in an expansion process. So, it means if we carry out the expansion process in a large number of steps, then we will observe a greatest value of work effect which will produce in the surroundings. So, now let us, after having a discussion of expansion process, let us now talk about compression process. The formula of work involved in the compression process is again the same, that is the work involved W equal to the P op, opposing pressure, that is the pressure which is being exerted on the system externally. This is opposing pressure times the change in volume. But now you should understand the change in volume is little different. Now, here the initial volume is V2 over here, and volume V1 is the final volume, that is we are allowing the system to compress from volume V2 to V1, that is this is exactly the opposite pressure. when we were carrying out expansion, we were altering the volume of system from volume V1 to V2, and now when we are trying to carry out compression process, we are trying to restore the volume of system, that is we are decreasing the volume of the system from its initial volume V2 to the final volume V1. So, although the same formula is being used, you can understand that V1, the final volume, is lesser than that of the initial volume V2. So, there will be a negative sign associated with the quantity which is involved in of volume which is involved inside the brackets. So, work effect value, the magnitude of work will have a negative sign automatically in this expression. So, before having a illustration of two-step compression process, let us first of all see how we achieved physically this single step compression process. Now, you see we have changed the place of these stoppers. Now, these stoppers are not present above the piston, but they are lying inside the system in order to have the position of the piston intact. And moreover, you can also see, compared to expansion process, a much larger mass object M is being placed over here. Why we have placed a much bigger mass object, I would just describe. But now let me say that we have also provided another set of stops, that is S dash. They are there to make sure that when the system undergoes compression, that is the volume of the system is decreased, it should decrease only to a volume element V1. That is, the boundary of the system should become intact when the volume changes from V1 to final state V1. So, this stopper S dash is serving that purpose. Now, we have already said that same expansion work formula is being used, but with a difference of position of V1 and V2. Now, V1 is final volume and V2 is the initial volume, which was opposite in the expansion process. More than this, there is another fact. Now, P op, as we have said that for any kind of work effect, there is a gradient of pressure is required, and if we want to compress the volume of the system, we need to apply greater external pressure in order to compress the system. That is, this pressure should be greater than that of the initial pressure, that is here P2, and that is P op should be greater than that of the P2 here, and it should be, moreover, it should be actually at the most it can be equal to P1, the final pressure of the system. So, it means that opposing pressure exerted by a mass object should be chosen by virtue of mass of the object, so that it is greater than P2 and is at the most equal to P1, the final pressure of the system. So, now let us see that if we have P op, which is very high over here, if you see, if you compare this compression process PV diagram with that of the single step expansion PV diagram, you will observe P op there was very less. However, P op opposing pressure over here is very high in order to observe compression. As a result, now you can see here the P op, at P op we can draw a dotted line, and below this dotted line we can shade the area from volume the V1 to V2, where V1 is the final volume and V2 is the initial volume. So, therefore, this whole shaded area represents the compression work or the work which was destroyed in the single step compression process. Now, you can understand, if we compare the single step expansion process work involved shaded area with that of single step compression process, the work shaded area is much more than that of the shaded area involved in the expansion process. So, therefore, we can say whatever the during the expansion process for same change in volume work is involved, there will be much more destruction of work during the during the restoration of the volume of the system again by virtue of the compression being done by virtue of compression work on the system. So, therefore, now let us switch over our attention to two-step compression. In two-step compression, again we will observe the compression in by virtue of changing in mass object in two steps. We will first of all put mass object which will exert lesser pressure as compared to the final pressure P2. So, P dash OP, that P op suppose is the pressure exerted by the first mass object, and the P2 which is the P double dash op which is the final pressure being exerted. So, P double dash op V dash is the this V dash is the final volume involved in the first step. So, therefore, we have given an expression. So, all we can say is that here shaded area, if you compare shaded area of the two-step compression process with that of shaded area in one-step compression process, you will see here the work involved in the two-step compression process is lesser than that of the work which was involved in the one-step compression process. And now, if we carry out the compression process is same number of infinite number of steps, multi-step compression, then again the shaded area you will observe that will be lying below, exactly below the PV expansion isotherm, which will be showing the initial and the final states. And over here you can see this shaded area that represents the work involved in the compression process during the multi-step compression is exactly the same that of the work which were produced in the expansion process if that work was done in a large number of infinite number of steps, that is multi-step expansion or multi-step compression. We observe same change in same work effects, that is however how much work is produced is exactly destroyed during compression. So, work produced in expansion process is exactly been the same as that of the work destroyed in the compression process if these expansion and compression processes are carried out in infinite number of, very large number of infinitesimal steps. Now, the question arises as to what all this has to do with the understanding of thermodynamic principles. Why we want to calculate the work involved in a multi-step expansion and compression process? Basically, you see it is the work and heat effects which are path functions which actually lead to calculation of important physical properties when a state change is being brought about. So, therefore, we need to calculate these properties, and work involved in multi-step or infinite number of infinitesimal steps, it is the maximum work which we observe in a expansion process, and it is the minimum work which we observe in the compression process, and both these work involved in when these processes are carried out in infinite number of infinitesimal steps, both these work effects are being the same. So, they set a limit on the they set a limit actually therefore on the expansion work and the compression work. And once the limit is set, now we can make an equations easier, which we will see in our further lectures what actually is the importance of these setting up of limits over to the expansion and compression processes. Now, having said this, let us now talk about thermodynamic reversibility or thermodynamically reversible processes. we always encounter with the question of what is thermodynamic reversibility, or in thermodynamic classrooms, it echoes a question, what is a thermodynamically reversible process? You see, it becomes a nightmare for a student to understand this. Reason being, he or she hasn't understood and correlated with the expansion work which we just described here. If you would have understood the expansion work over here, you will be able to correlate with my subsequent explanation towards the thermodynamic reversibility. Let us now consider first of all the expansion work which we did in just one single step. The work involved, there was some work involved shown by the shaded area. Now, if we compare the work involved in this expansion process, that is smaller as compared to the work involved in the compression process. So, therefore, work which got produced in the expansion process, that was lesser as compared to the work which got destroyed in the compression process. So, therefore, if we suppose first of all expand the system in a single step from volume V1 to V2 and then compress the system back from volume V2 to restore it to its initial volume V1, if we do it in a single step in this course of the process, we can see that net amount of work will be destroyed. Why? Because during expansion less work was produced and during compression more work was destroyed. So, therefore, there was a net effect is that net work was destroyed if we carry out the process in just single step, both these processes of a cyclic process. Now, let us consider another situation, the multi-step expansion and compression process. You see, you would have appreciated the fact that when we did carry out the expansion work in infinite number of infinitesimal steps, there was the work which was produced that was exactly the shaded area beneath the PV expansion curve between the limits initial volume to the final volume. That work involved during the expansion process, that was exactly equal to the work involved or work destroyed, you can say, during the compression process. Reason being that the work was done in infinite number of, very large number of steps, and at each step very small volume element was changing, and at each step very small work was done, and we can graphically interpret it that when we carry out our expansion and compression work to restore the system back to its initial state, therefore, we consider a cyclic process, then in that situation work effect will be 0, no net work either will be produced or will be destroyed. If we first carry out expansion process in infinite number of infinitesimal steps and then we restore the system by virtue of compression process, that is also again in infinite number of infinitesimal steps. In that manner, there is neither the work destroyed nor the work is produced finally when the system is restored. So, since no net work effect is produced in the surrounding, so therefore, we can see neither the surrounding has observed some change nor the system has observed some change in terms of some thermodynamic properties. So, therefore, the stage is set now with this example how to describe a thermodynamically reversible process. You see, we can say that a thermodynamically reversible process is the one which proceeds in infinite number of infinitesimal steps such that both the system and the surrounding deviates from, or you can say remain in internal equilibrium with each other. There is very small difference between the opposing and the internal pressure of the system. So, a reversible process is the one which when carried out in infinite number of infinitesimal steps, such that both the system and the surroundings remain nearly equal, nearly in equilibrium with each other. More importantly is the fact, when suppose the same system is restored back to its initial state by following the same sequence of steps in a reverse manner, then in that situation not only the system gets restored, but also the surrounding gets restored. So, in a cyclic process, if we carry out some forward sequence of steps and restore the system back by following the same sequence of steps in the reverse order, in this manner if we restore the system, then the surrounding also gets restored, then we say the process is reversible in nature. That is, there has been no net change is been observed neither in the system nor in the surroundings. And the characteristic of these processes are what? The main characteristic is that these processes you can see by virtue of consideration of multi-step expansion and compression process, these processes are followed in infinite number of infinitesimal steps 1. By virtue of this infinite number of infinitesimal steps is that we can say there is a very small difference between the driving force and the opposing force, that is the internal pressure and the external pressure. In the expansion process, the external pressure was very infinitesimally lesser at each step, whereas in the compression process the opposing pressure was infinitesimally smaller than that of the internal pressure. So, thermodynamically process, once again let us recall what is a thermodynamically reversible process. A thermodynamically reversible process is the one which which is carried out in infinite number of infinitesimal steps, and following some sequence of steps when the system reaches the final state. When this system from its final state is restored back to its initial state by following the same sequence of steps in the reverse manner, while restoring the system in this way, the surrounding also gets restored, then we say the process which we carried out is thermodynamically reversible in nature. So, now on I do believe that there should not be any ambiguity about the thermodynamically reversible process or thermodynamic reversibility, because this is an important topic at which students always feel difficulty at. But it is very simple to understand, as I said earlier. If you carry out some sequence of steps, your system do something and then reaches a final state. Now, if you try to restore the system back to its initial state, you can check whether the process was reversible or not. When you carry out the same sequence of steps in the reverse order, in this manner when you restore the system, when the surrounding also gets restored, you can say the process is thermodynamically reversible in nature. This is how, in very simple terms, very layman's words, we can define the thermodynamically reversible processes. Now, it is important to understand the difference between the irreversible and thermodynamically reversible process. You see, the one-step compression process, one-step expansion process, all those processes were done in just one step, two step, and you could appreciate the fact that only a finite length of time would be required, right? But if you carry out the expansion of compression process in infinite number of infinitesimal steps, then consider the situation when you take the term infinity into account. It means a very large amount of time would be required, infinite length of time would be required for completion of the process. So, therefore, in terms of practicality, this is not practically viable to carry out a process infinitely slowly and infinite number of steps by virtue of changing the opposing pressure, by changing the mass objects which is having a very small difference in their masses. So, therefore, what does it mean? Does it mean that thermodynamically reversible process which we have just defined here has no meaning. No, it is not. Thermodynamically reversible processes are important ones because they set the limits as to how much maximum or minimum quantities of work effects which we can observe. And these limits are important to understand as to what are the abilities of the system, to what extent it can give you some observations, that is how much maximum amount of work it can produce or how much minimum amount of work can be destroyed upon the while working on the system. So, these are, that is why thermodynamically reversible processes are important, but these are, as I said earlier, as infinite length of time would be required for their completion. So, therefore, these are not practical processes, these are only these are only in consideration, and since they are only in consideration, so we just say that these are ideal processes, these are not real processes. Real processes are irreversible processes. But the fact of matter is that the goal of reversibility in the real processes can be approached. We can, of course, we can do same expansion work, if not in infinite number of steps, then of course in a very large number of steps. Then in that situation we can say that we can approach the goal of thermodynamic reversibility in a thermodynamic process in reality, but we cannot actually completely attain it. We may attain it to the extent of 90% goal of reversibility, 95%, 98%, 99% or so, but to complete extent, that is 100% goal of reversibility cannot be attained. The goal of reversibility can only be approached to a certain extent. Now, having said this, let us have an illustration of an activity by virtue of which you can understand what we mean to say by the thermodynamically reversible process. Let us now consider we can have a cylinder upon which we can have a piston, that is a piston system, piston cylinder arrangement within which it encloses some gas. We can put a platform on the piston. On the platform on the piston we can put a number of coins, very large number of coins over here, and in nearby we can put another platform near the piston system, piston cylinder arrangement, and here also we can place a large number of coins, but just one coin less than that of the number of coins which were placed on the platform being built on the piston. So, now when we slide a coin from the piston all to the nearby platform, what it will do? It will decrease the mass of the mass object, that is the number of coins by virtue of number of coins on the piston. So, this will lead to a very small difference between the internal and external pressure. So, internal pressure, since it will be just slightly greater than that of internal pressure, what you will observe? You will observe expansion. And now if you try to restore the same system by placing one coin from the nearby platform to the piston again, now what you will observe? Again a gradient of pressure. The external pressure will be slightly greater than that of the initial pressure, and you will observe compression. While doing so, it does mean that no work effect was produced. So, this activity nearly illustrates the thermodynamically reversible process, but it is not an actual reality. Why? Because you have performed some work in sliding the coins while you were putting the coin from the nearby platform to the number of coins placed on the piston. So, with this, let us describe what we will cover next. In the next lecture, we will have the discussion of first law of thermodynamics. So, in nutshell, let us say we have described what is work, we have described what is heat. Now, when this is the interplay of interaction of work and heat with that of the system, which leads to the increasing or decreasing, an increase or decrease in the internal energy of the system. An account of all this is only the first law of thermodynamics, which we will study later. Thank you so very much.
With this note, thank you, sir. Thank you so very much for giving us once again a very productive session. Dear friends, if you have any question regarding this particular topic, or if you want to give your feedback, then you can mail us at info.cec@nic.in, and very nearly, in future sessions, we would be discussing more on the chemical thermodynamics. So once again, thank you, sir. Thank you once
very
again.
much.